Okay, good. So the first of the three lectures is maybe a little on the introductory side, I guess. I think probably a lot of you, maybe all of you know most of everything I'm going to say in this lecture, but I wanted to just put a kind of a baseline for our discussion on cosmology. So my intention was to give a lecture on both classical and quantum cosmology. The first half is really going to be focused on classical cosmology, and the second on quantum cosmology, but I wouldn't say that I'm an expert, the kind of expert that gives a master class on quantum cosmology, so my remarks will be a little bit sketchier there. But the kind of theme that links these two parts of the lecture together is both kind of historical and epistemological in character. So, and the reason for that is it's going to lead into the future lectures, especially the last one when I talk about meta-empirical theory assessment. Okay, so let's start though with just to clarify some terminology. So cosmology can be called the science of the universe. It studies the origin, evolution, destiny, the large-scale physical structure of the universe. This textbook was my introduction to cosmology by Edward Harrison. I don't know if anyone's seen this one, but I think it's a great book. It's by a physicist, but one that thinks in a somewhat philosophical and historical way. So that's where I get this phrase, the science of the universe, or many people have used it. Okay, so I mean, just on the face of it, classical cosmology would seem to refer to cosmology restricted to methods of classical physics, especially relativity theory, and then quantum cosmology might seem to refer to cosmology done using quantum physics, but there's kind of two different senses one could have by this term quantum cosmology. So in a very broad sense, it could be referring to any cosmology that utilizes quantum theory in addition to classical theory. It also might be meant in a narrower sense, quantum cosmology referring to fully quantum cosmology, one that relies on in particular a theory of quantum gravity. So that's the kind of quantum cosmology that, say, Butterfield and Isham have in mind in their paper on the subject. The endeavor of quantum gravity is closely related to quantum cosmology, the attempt to have a quantum theory of the whole universe. Okay, so I bring this terminological stuff up in point because when preparing this lecture I came across this recent paper of Wallace's that probably many of you know on low energy quantum gravity. And there he starts out the paper taking philosophers and physicists to task for making false claims about the nature and status of quantum gravity. So he says, if quantum gravity indeed just means a theory that combines quantum mechanics with general relativity, then we have a fairly satisfactory theory of quantum gravity already, namely semi-classical gravity, quantum field theory on curved spacetime, or similar kind of, classical theories that have been supplemented with quantum theory, like what gravity is an effective field theory, for example. So he distinguishes these versions of low-energy quantum gravity then in a broad sense from a UV complete quantum gravity or something similar, or quantum gravity in a narrow sense, or we might call it a quantum theory of gravity. So in this paper, we might think that what he has to say about quantum gravity really just boils down to kind of making a semantic dispute. It does have some bearing based on the scope of philosophical research on quantum gravity, and we can make a related point then about quantum cosmology. And so the reason I bring this up now is because our workshop here is about quantum cosmology, but we have to think a little bit about how we're going to use that term, what the scope of it is. So I'm generally going to be thinking of it from a fairly broad scope because I haven't really worked on quantum gravity in this narrow sense. When I've worked on stuff on cosmology, it's generally cosmology from either a purely classical point of view or one that supplements it with some methods of quantum mechanics, especially in connection to inflationary theory. Okay? Yeah, so that's what I'm saying here. We might want to distinguish senses of quantum cosmology in a similar way. So, of course, if we think of quantum cosmology in the broad sense, then people have been doing quantum cosmology since the 1940s or so, because of the use of atomic physics in establishing the Big Bang model, as I'll talk about a little later. But of course, a lot of you are interested in quantum gravity and its connection and quantum cosmology in the narrower sense. And so there's a separate set of questions and motivations that I think are connected with that. And that all of this, I think, should fall within the scope of our project here. Okay? Right, so let's see. Yeah, I don't need to say anything more there. So that's just a kind of prelude then to how I'm going to be talking about cosmology in these lectures. So for today's lecture in particular, I'm going to cover cosmology, quantum cosmology in the broad sense in the first part. So first I'll talk about general relativity and its application to cosmology in a historical vein, starting with Einstein's original static model of the universe, and go through the development of cosmology up to the present, or at least I think I don't go quite up to the present in this lecture, because I'll save what I have to say about inflation for the next lecture. And in the second half, I don't have a whole lot to say about quantum gravity and quantum cosmology in the narrow sense, because this has not really been an area of my research. But continuing on the kind of epistemological orientation of the earlier part of the lecture, I want to say some remarks about that in connection with quantum gravity and quantum cosmology too, in particular the use of the guiding principles, which Kiefer and Niels have talked about in their papers a little bit. So I want to say some things about that, as also a kind of prelude to the last lecture on meta-empirical assessment. Okay, so let's get into it. So general relativity theory, probably most of you are quite familiar with. So one way to describe it is as a classical field theory that's perspicuously formulated with differential geometry. Okay, so the classic field at the heart of general relativity is the metric field, usually denoted with the letter G. It's defined on the four-dimensional differential manifold M. These are some mathematical details that don't matter so much, except for setting up the Einstein field equation here at the bottom. Of course, the tensor, each point of the manifold is Lorentzian. This determines the famous light cone structure of the space-time, and so on. Okay, so for every field theory, we have some dynamical field equation. For general relativity, it's the Einstein field equation. It relates the matter contents of space-time, which is represented by this tensor field T, usually denoted, to some geometrical objects, the Riemann curvature, the Ricci scalar. These are formed out of the metric G, or more precisely out of the Levi-Civita connection. But anyway, we are, for the purposes of cosmology, going to add the cosmological constant lambda in here, and then we get the Einstein field equation here at the bottom. Okay, so that's just general relativity, the basics. General relativity, though, gets applied to cosmology, and most cosmological models are based on general relativity. But why use general relativity to model the universe as a whole? There are various arguments you can make. Best argument probably that we can make is an empirical one, but if we want to make a sort of modern, sort of theoretical argument, it might look something like this. When we consider all the possible forces that we're aware of, the four forces that stand out are the strong and weak nuclear forces, electromagnetism and gravity. But we wouldn't expect short-range forces to play a direct role, so to speak, in cosmology, because they're short-range forces. They can't be directly responsible for the dynamics of large-scale structures in the universe. Electromagnetism and gravitation, on the other hand, are long-range forces. They could, in principle, be theoretically important to cosmological dynamics, but plausibly, electromagnetism is irrelevant, as one would observe in the large scale of the universe, annihilation and repulsion effects, and we don't see those. In any case, macroscopic bodies tend to be electrically neutral as well, so we shouldn't expect electromagnetism to play a big role on large-scale dynamics of the universe. But gravity is plausibly relevant. Gravitational attraction is observed on large scales, cannot be shielded, and so on. So since our best theory of gravity is general relativity, and only gravity seems relevant on cosmological scales, it makes sense to model cosmological models on the models of general relativity. Okay, so that's a kind of argument. It's a fairly good argument, but from a historical and more inductivist point of view, the application of general relativity to the universe at large is quite an enormous extrapolation beyond the regime in which the theory has been tested. Yeah. So from a more empirical point of view, it seems like it's kind of a big leap. Okay? So when we think through the history of testing of general relativity, back in the early 20th century, Einstein had at his disposal relatively little empirical experimental results related to gravity. So he had some laboratory-based experiments, and he had the check, this famous check on his theory with the precession of perihelion of Mercury. And then his prediction that he developed out of the theory of the bending of light and gravitational fields was put to test shortly after the development of the theory. Then in the 60s, there were some further important tests made of gravitational redshift that played a role in confirming general relativity, relativistic time delay, observations of binary pulsars, all further added to the evidence. But again, most of these tests are restricted to the solar system scale tests, not to the cosmological scale. So even in the 1990s, when here I'm quoting from Peebles' book on the sort of confirmation of the standard model of cosmology that came out some years ago. Yeah, he says there were even in the 1990s, when there were demanding checks of the predictions of general relativity on scales ranging from the laboratory to the solar system, probing out to around 10 to the 13th power centimeters. The application to cosmology on the scale of the Hubble length, 10 to the 28, extrapolates from the precision tests by some 15 orders of magnitude in the length scale. So this is just to say that general relativity applied to cosmology from a more experimental point of view is an enormous extrapolation, even if we can convince ourselves on the basis of some theoretical arguments. Yeah?
Can you just ask a question?
I suppose, yeah.
So for instance, Ellis, I think, likes to make this claim that maybe 100 or so just as well accounts for the observations as GR does. And yeah, I don't know. You come across claims like this, what do you think of them? Have you heard this particular?
No, this is part of a lot of experimentalists' interest, I think, in sort of testing general relativity to more stringent standards, because there seem to be theoretical alternatives. It's something we can discuss. For sure. Okay, so let's go on. So now I want to, that's the sort of first step is, if we want to develop cosmological models, we need some sort of theoretical framework to do it in. General relativity is that framework, but we can make some theoretical arguments for it. But if we think more from a very inductivist, experimentalist point of view, it is quite an enormous extrapolation. Maybe it's amazing that it's so successful as it is. Anyway, going back to some specific cosmological models that were developed in the 20th century, the first one is Einstein's static model of the universe. So his was the first attempt to apply in 2017, shortly after the development of general relativity, the final development of it. He published a paper to apply his theory to cosmology. The model introduced in that paper has come to be called the Einstein static model. So he essentially required two conditions to pick out this model. First is that spacetime is spatially homogeneous and isotropic. The second is that spacetime is static. So the first condition entails that the matter contents of the spacetime can be represented as a perfect fluid with a pressure P and an energy density rho. So if you make this first assumption, that reduces the Einstein field equation to two simple coupled equations, which come to be called the Friedmann equations. Okay, so sometimes just the first one I've written here is called the Friedmann equation, sometimes both the Friedmann equations. The first one is kind of, we can think of as the energy equation. The other one's sometimes called the acceleration equation. In general, it's derived from the Rank-Drury equation, so it's the Friedmann version of the Rank-Drury equation. In any case, there's some symbols here, but this is just to say, like, the more complicated Einstein field equation, which could be represented in coordinates as like 16 equations or so, reduces quite a bit under the symmetry assumption, number one there. Okay, so I've written H here to represent the so-called Hubble constant or Hubble parameter. Geometrically, we could treat it as a spatially homogeneous scalar field, and it represents the expansion of space. So the small kappa, that represents the curvature of space. And so, in general, relativistic spacetimes that satisfy this first condition only are now called Friedmann-Robertson-Walker spacetimes, or Friedmann-Robertson-Walker spacetimes. I'm probably just going to say FRW from now on. These equations with just this first condition satisfy really the basis of the standard models of contemporary cosmology, like the Hot Big Bang model, concordance model. Okay, but Einstein added the second condition. He required space-time static. So that second condition is equivalent to setting the Hubble constant to 0, right? It doesn't change. The space-time doesn't expand, it doesn't contract. Okay, so this reduces the Friedmann equations a bit further to this form. Very simple then, right? There's just a term with the curvature there. So Einstein, actually considers a further condition. He requires that the perfect fluid be dust, so that's matter without pressure in cosmological lingo. And in that case, we find that the curvature of space is necessarily positive, right? We could do some algebra and see that kappa is equal to 4 pi rho. So this implies, I mean, with some assumptions about what dust is, the strong energy condition, and we get that kappa here has to be positive. So Einstein's static spacetime is a spherically symmetric spacetime with positive curvature. Okay? Another facet, though, that turns out to be historically important is that given these conditions, the cosmological constant, which Einstein introduced in this paper, has to be finely tuned to equal precisely kappa at every time. And this makes the model, in a sense, dynamically unstable. So Einstein didn't realize this, maybe surprisingly, at first when he wrote this paper, but it was pointed out by Eddington, and at this point Einstein realized that this was thought that this was a serious theoretical flaw of the model, and he decided to abandon it in favor of an expanding FRW model. He thought, theoretically or philosophically, one might say that space-time had to be static in this way. He disliked the idea of a universe a space that was expanding and contracting for other philosophical reasons. Okay, but he realized that, he decided that this was quite a theoretical flaw and gave up his insistence on this static condition. Okay, so just to rehearse, I'm going to move on to the de Sitter model here in a second, but in the Einstein static model, I want to kind of key in on Einstein's motivations here. He actually doesn't say very much, I think, in his papers about motivation for number one, but the second one is kind of just a theoretical preference in a way that Einstein made. So one thing that, Einstein really wasn't that interested in experimental physics of the time, so even though at the time people were aware of like galaxy surveys and so on showing that the spectra of galaxies was all redshifted, which suggests an expanding universe. Einstein was actually not interested in these kind of things. He was mostly moved more by certain theoretical or maybe even aesthetic motivations. Okay, a contrasting model is the one developed by de Sitter around the same time as Einstein. He published a series of papers in 1917, 1918 or so. So in the 1920s, these two models really dominated discussion. For one reason, not very many people were working in cosmology at the time. Another, though, is it's somewhat difficult to find exact solutions to the Einstein field equation. But de Sitter assumed a highly symmetric model and posed it as an alternative to Einstein, a contrasting model. Okay, so here, de Sitter's model is homogeneous and isotropic as well, strong symmetry assumption, just like Einstein's, but he assumes that this spacetime is a vacuum spacetime, and so the stress energy is equal to 0. Okay, so that also greatly simplifies the model, but he does keep the cosmological constant. So in this case, the Friedmann equation is reduced to these two very simple ones. So given all the kind of symmetries, we can sort of slice up de Sitter spacetime in various ways. One foliation that we can choose is one that makes the curvature 0. So we can set kappa equal to 0 in this foliation of the spacetime. And in this case, with a little bit of algebra, you can see that the Hubble constant is constant in time and proportional to the root of the cosmological constant. So what that means is that geodesics in the spacetime diverge from one another exponentially in time. Right? So that this is an exponentially expanding spacetime. The expansion is happening in time, but spatially it's exponential. Okay, so this has been a famous model as well, used for various purposes that I'm sure de Sitter couldn't have anticipated. But in any case, like I say in the first part here, these two spacetimes were sort of set up as contrasting possible models in the 20s. So, although evidently, obviously, the universe is full of matter, and de Sitter's universe lacks matter, still we can imagine that there's so little matter in the universe that maybe a vacuum space-time is an okay model of our actual universe. And if we allow that, then we can argue that de Sitter's universe makes a stronger connection to the available cosmological observations at that time. So like I said, Slipher, I didn't mention Slipher before, but in 1917 in particular, I think Slipher made a number of observations showing redshifting in the spectral lines of galaxies, and this is naturally interpreted as being due to spatial expansion of the universe. And then, of course, in the 20s, the more famous observations by Hubble further improved the evidence for this spatial expansion in the universe. So, as I said before, Einstein was generally unaware of the latest observational results in astronomy, and he relied more on his intuition about the nature of the universe, in particular holding philosophically that it was static and spatially finite. So like I said, with that positive curvature of the Einstein static universe, this leads to a spatially finite universe, whereas if we allowed the curvature to be zero, we would have to have an infinite universe, spatially infinite universe. Okay, so but he gave up on his model, I think 1927 or something like that, convinced that the dynamical instability was theoretically unacceptable. Okay. Yeah, another remark though is that both other cosmologies were past and future infinite, so the universe has to be an object that's always existing. And that's in contrast to the models that came to replace these as viable models of cosmology. So the Lemaitre-inspired expanding universe models superseded both of these in the 1930s and thereafter and became the dominant models. Of course, the Lemaitre-inspired models, the FRW models, are past finite. There's a beginning point to the universe, as it were. Okay, so moving a bit forward through the history, maybe I should emphasize that in this phase in the 1920s and into the 1930s, a lot of theoretical motivations were pushing the preferences for various models because there was relatively little empirical evidence available to distinguish between them or guide the development of future cosmological models. Yeah, things remain this way in the 1940s and 50s and 60s, where the big debate in that period of time was between the steady state model and the Big Bang models. So the steady state model was developed first in the, I think, late 1940s and further over the 50s and 60s, in particular developed by Bondi, Gold, and Boyle. And then the successor to Lemaitre's expanding universe idea came to be called the Big Bang model. I think maybe Hoyle came up with that name, but I forget exactly who. And Gamow played a particularly important role in the further development of this model and its physical content, particularly in relation to the matter contents of the universe. So the steady state model accepted the spatial expansion of the universe. Everyone pretty much accepted that idea at this time. But according to the steady state model, the appearance of the universe nevertheless doesn't change over time. In this way, it could preserve the idea that the universe is past and future infinite, unlike the Big Bang model, FRW models. In order to make this work, though, the developers of the model had to suppose that matter was continuously created in the universe in order to supplement the depleting matter due to spatial expansion. So that was the basic idea of the steady state model. It had a particularly strong symmetry assumption behind it called the perfect cosmological principle. I'm not going to talk about the cosmological principle and the Copernican principle today, though, even though those are kind of relevant to thinking about the development of cosmology here. I think it would just be too much for this lecture. Anyway, moving to the Big Bang model. So Gamow in particular, so he was the only one working on Big Bang physics at the time, but he played a pretty prominent role in the development, maybe the most prominent role in the development of the Big Bang model. So he wanted to connect the developing nuclear physics at the time to cosmology. And one of the important motivations was identifying light element abundances in the universe through a process called Big Bang nucleosynthesis. Okay? So then when astronomers went out and looked for the spectra of light elements, they could sort of use that as a sort of empirical check on predictions of cosmological models based on atomic physics, like the Big Bang model was in nucleosynthesis. And so that was an important confirmation of the model, empirical confirmation of the model. Probably the one that people point to most is that what really clinched the victory, as it were, for the Big Bang model was the discovery of the cosmic microwave background radiation, or CMB as they'll probably say from now on, in 1964. And this led probably most cosmologists to accept that the Big Bang model was basically correct. The number of people working on the steady-state model dropped off quite a bit after that. People still continue to work through all the way through the 90s. Maybe some people still do now, I don't know. But definitely the Big Bang sort of solidified itself as the standard model of cosmology at this point. Okay, and that brings us now up to today's model, called the lambda CDM model or concordance model. So the Big Bang model has held up pretty well since the 1960s. It really is the basis of the standard model of today too. But after the 1960s, there was still work to be done by astronomers and cosmologists, in particular to fix certain important parameters of the model. The Hubble and deceleration parameters. So the Hubble one I introduced, the deceleration one comes out of some of those equations I showed before, but I'm not going to show you that. Basically, though, there were these two sort of parameters that observations could fix, and a big challenge for astronomers from the 1960s on was to figure out exactly what these parameters were. These would determine, for example, whether the universe was spatially infinite or finite, and things like that, what the fate of the universe would be, is there going to be just a continual expansion, will there be a recollapse, something like that. And during this period of time, cosmology even came to be known as a search for two numbers, these two numbers here. But the model, the Big Bang model, underwent some changes as observations challenged this sort of simple assumptions of the model. So in the 1970s, the idea of dark matter was introduced to account for galactic dynamics that couldn't be accounted for with normal matter. And now it's acknowledged to account for around 25% of the current energy density of the universe. So this dark matter is cool dark matter rather than hot dark matter, hence CDM in the title, lambda CDM. And then more recently, evidence from supernovae indicates that the expansion of the universe is in fact accelerating, and that wouldn't be possible with normal matter or dark matter for that matter as the sole constituents of the universe. So it was recognized that this acceleration could be accounted for by reintroducing the cosmological constant into the equations, the Friedmann equations. So after the Big Bang model got established, that lambda had actually dropped out of the picture. I forgot to mention that. But yeah, generally it was seen as a possible parameter to reintroduce in order to account for this accelerating effect. Okay? But more generally, we could imagine something that doesn't function exactly like a cosmological constant that causes the universe to expand in the way that observations suggest. And so generally the term dark energy has been coined for the responsible agent for this expansion. Okay, and then finally, so that's why the lambda is in there. But there's a third component of standard cosmology. It's generally considered part of the standard cosmology, I suppose. That is inflation. So inflation provides a mechanism that plays an important role for the empirical basis of the model. So the universe is obviously inhomogeneous to a certain degree, and one thing we would like to understand in cosmology is how structure formation, the formation of galaxies and other sort of large-scale structures occurs. And inflation, one of the functions of inflation is to give a mechanism for seeing these inhomogeneities that account for structural formation in the universe. That's important to note, though, that initial motivations were not for that. They were for different things, solutions to various fine-tuning problems of the Big Bang model, problems known as like the horizon problem, the flatness problem, the monopole problem. And these I'll talk about tomorrow.
Okay, so, two questions.
Yeah.
One is a boring semantic question. So the hot Big Bang model is different from the lambda CDM or concordance model in that it lacks these three parts. No dark matter, no dark energy, no inflation.
You could say that, yeah.
Is that
That's how I would use those terms.
Okay.
Other people might use them slightly different.
Lambda CDM, concordance model and standard model are the same thing, though.
I would say, yeah. Possibly some people distinguish between those, but my sense is that these are interchangeable.
Okay. And the more interesting question is, what about these seeding inhomogeneities that are needed for structure formation? Is inflation the only?
I'll talk about that tomorrow.
Okay,
Yeah.
because I think that's a very interesting question.
Yeah, absolutely. Yeah, I'm not going to talk about inflation anymore in this talk, but that will be the main topic for tomorrow.
That's the shift for tomorrow.
Yeah. Okay.
And
All right. Yeah.
So steady-state model always was open for, so the steady-state model was always open for spatial expansion, where some people also thinking it even has to be of the same size, so to speak.
Yeah, I think that's right. Yeah. So, I mean, they accept that spatial expansion happens, but spatial expansion in the FRW model would require, I mean, there's like a past singularity basically, which limits how far back in time you can go. That they rejected. In order to combine spatial expansion with a past infinite universe, they had to come up with something that allowed that to happen. So continuous matter creation was the solution that was hit on the basis of the steady state model.
That was a stupid question, but sorry. Which models are these? Which heuristic models would be typical of steady state?
No, I don't know that.
Yeah, okay, it's just...
I mean, I think it's a modification of general relativity that you have to make, though, in order for it to work. But yeah, I don't know the details enough to say like how it works. Okay, so just to kind of summarize the various theoretical and empirical motivations that played a role in the development of standard cosmology. I think we have some motivations that come from our expectations about the applicability of the theory. So we expect that general relativity is universally applicable. That has consequences for how we use that theory to model systems. Okay? And so because we think general relativity is universally applicable, we think it applies to cosmology, and so we have relativistic cosmology. Certain other motivations come from assumptions we want to make about the models in that theory that we think apply to the system. So, for example, Einstein wanted the universe to be finite in space, and because of those kind of assumptions, you end up with universes like the Einstein static universe, or more generally, the universe is spatially closed. Ideas about the infinitude of time, like whether the model is past and future infinite or not. Those kind of assumptions, theoretical assumptions, lead to consequences for our models, like the Einstein static universe is one, which is infinite in times, future and past. Also the steady-state universe, as we were just talking about, has this character. We might have certain assumptions about what spatial curvature should be like. That assumption is problematized in the flatness problem that I'll talk about tomorrow. Einstein assumed that a model had to be stable, and because of that rejected the Einstein static universe. And some further problems that I'm going to talk about tomorrow about causal contact leading to the horizon problem, homogeneity, leading to a kind of uniformity problem as well. But I think if we look at most of these assumptions, most of these have kind of proven false or are not very well motivated in the end. Much stronger models, assumptions, or not really assumptions, but results, empirical results that have shaped standard cosmology have come from observations of redshifted galaxies, which suggest that we need to model universes expanding spatially. One that I didn't talk about, and it's seldom talked about, is the problem posed about why the night sky is dark at night. If the universe were like a Newtonian one with stars everywhere, then the night shouldn't be bright at all. There should be light coming at us from every direction. But the expanding universe plays a role in solving that paradox, which is known as Olber's paradox. Similarly, observations of light element abundances were important confirming evidence of the Big Bang model. Similarly with the CMB, isotropy is something that we can observe, which is a strong symmetry assumption that we can apply to general relativistic models. So the FRW models are spatially isotropic, but there's a generally, a larger class of spherically symmetric models that relativists have investigated over time too to see whether they're applicable to the universe. A lot of these have, I think, like fine-tuning problems, so generally they're not considered viable models. And then, like I mentioned, accelerated expansion, galaxy rotation curves. Okay, yeah. So the point here is just that empirical motivations have played a pretty enormous role, I think, when you look at the history in shaping what standard cosmology is like, and a lot of theoretical assumptions have proven to be sort of off. As it were. Do you have a question?
Yes, about the spatial curvature flatness.
Yeah.
Isn't that also something that's in some sense observed?
Yeah, but with the assumption of a model, of course.
Yes.
Similarly, homogeneity is something that's an inference. I mean, so for example, we can observe from our place here on Earth that the universe looks the same in every direction, so it seems isotropic. How do you go from isotropy to homogeneity, same everywhere in space? Well, one way is to assume the Copernican principle, which is to say it's pretty unlikely that we're at a privileged place in the universe. So if it's isotropic here, it's probably isotropic elsewhere. If it's isotropic everywhere, then it's homogeneous. So homogeneity is pretty close. You have relatively minor assumptions, theoretical assumptions to make to get homogeneity. And similarly, with flatness is more theoretical assumptions, but once we're convinced that the Big Bang model is a good model to model all these other things, then that fixes the necessity for very close to flatness. Yeah, so it's definitely not like an either or just pure, we couldn't have a purely empirical model of the universe. It wouldn't be very informative anyway. But a lot of these assumptions seem to be like purely theoretical. Like there's no good evidential reasons to assume any of those first conditions. Like general relativity permits all of these conditions and they're opposites. So we don't know until we have some stronger evidence about which way to go on them. And now we do, like most of these things are quite fixed, evidentially. Okay, so this is like the midpoint of the talk. Maybe it's a bit more than the midpoint. So are there any other questions before we move on to talk a little bit about quantum gravity?
What does type 1a SN stand for?
Type 1a SN. SN is supernova. 1a is just a certain type of supernova in a classification of supernovae.
Conversely, we could say that these empirical motivations are also not theoretically completely innocent. I mean, some more than others, but there are certain modeling assumptions which are also made there.
Yeah, and this is a very crude slide that I made to try to summarize what I've been saying before, but it is, I wanted to at least put something like this up because it's going to play a role in the future lectures as well. How like, empirical and theoretical motivations, basically which ones are worth making and which ones aren't, and how the interplay of theory and experiment is important, whereas if we just do one or the other, then our motivations for models sometimes lead us astray, as I think some of the early models did. Okay, I'll go on. All right, so now moving to quantum cosmology. Well, if we take quantum cosmology in the narrow sense, like quantum cosmology founded on a theory of quantum gravity, and speaking of quantum gravity, the questions that people always seem to ask at the start of an investigation into quantum theory of gravity is whether anyone should do it. Yeah, it's Chris' paper. Like all these titles sort of suggest these questions. Do we need to find a quantum theory of gravity? Is quantum gravity necessary? Can quantum gravity be avoided? And so on. So, I don't know, a quick answer to that question is why not? Give it a try, right? So,
in that literature, that was not contested, but you could ask why not.
Of course, I know.
It was more like a logical point.
Yeah.
But how strongly is it forced upon us, I guess?
Yeah. So how strongly is it forced upon us?
I'm not sure all these authors agree. I think the general consensus is that there's no logical or near logical necessity.
Yeah.
There could be perfectly consistent models of some sort of, in some sense, classical gravity mixing or being combined with quantum theories of the other forces. But that doesn't mean that there's no physically good reasons to do it, of course.
Yeah. Yeah. So if we, that was it. So if we accept, though, that if we do this kind of research and develop various theories of quantum gravity, then just like how we had a development of a general theory of relativity and had reasons to apply that to cosmology, similarly, we might think once we have a quantum theory of gravity, it's very natural to try to apply it to model the universe quantum mechanically. And yeah, this is, I pulled some quotes from a Butterfield and Isham paper where they discuss quantum cosmology. As they point out here, they're closely related but different. They do point out, though, that it doesn't necessarily involve the idea of a theory of the whole universe, and we could have a quantum cosmology in the broad sense as well. As they point out, we talk about quantum focuses on physics of black holes. But in general, in quantum cosmology, I think here in the narrow sense, one seeks quantum theoretical cosmology, a theory of the whole universe. And I think in the literature, stretching back decades, when people say quantum cosmology, they usually mean something like this. But they point out in their paper one of the frequent motivations people make for a quantum cosmology, the interest in finding a theoretical framework that avoids the mathematical singularity that is inevitably in the account of Big Bang cosmology given by classical general relativity. So there's a theoretical motivation, like on that previous slide where I had the table, here we see like a frequent theoretical motivation that I think would fall in that sort of second class, a motivation that is the purely theoretical one that doesn't have, well, maybe not purely theoretical, but a fairly theoretical motivation. So that's kind of a motivation coming from a class of models to a motivation from the class of models back to the kind of theory that we want. Oops, I thought I had. Oh, that comes a little bit later. Sorry, I thought I moved this slide away. Anyway, so like I'm not an expert on quantum gravity, and so when I was preparing for this lecture, I kind of wanted to say a little bit more than I'm going to about quantum gravity. But one of the papers that I revisited that I remember reading when I was a PhD student was this paper by Butterfield and Isham, where they give a typology of means of obtaining the quantum theory of gravity. I think it was interesting. I thought it was interesting for me to put this up here to think about, well, first of all, like the wide range of models that exist now that didn't exist at a time that this is the 2001 paper, I think. So in 25 years, I was kind of curious, like to what extent you can fit even modern programs in quantum gravity in this classification, and whether it's a good one. I'll say that in the next slide. But anyway, this is sort of their original typology of quantum theories of gravity, more like how to get them, the means of obtaining them. So one, quantized general relativity. That's clearly the kind of thing that canonical covariant quantization programs try to do, more or less, I guess. Yeah. Second is thinking of quantizing a different classical theory, like we would do with string theory, where you obtain general relativity in a particular low energy or classical limit. The third category is taking general relativity as the low energy limit of a quantum theory that isn't a quantization of classical theory. They didn't give any examples, I think, in their paper at the time, so I don't know exactly what they had in mind. But there's a few things that you might think to fit into this category. I listed some examples that seem to fit to me. And then finally, they start ab initio with a radically new theory. And again, they didn't give any examples, so I didn't know exactly what they had in mind. But some modern programs you could think of sort of fitting in this category too. Categories 3 and 4 seem kind of similar in a lot of ways, but in any case, yeah, here's a typology, and I think I found this interesting. Like I've been in this lecture, I'm trying to think about motivations, theoretical and empirical motivations for theories and models and so on. And there's certainly some kind of theoretical motivations that even come into coming up with a typology of this kind. Like generally, it's very based on the idea that quantization is how we develop quantum theories. That seems to be a big kind of background assumption here. I think from, maybe they could have been, maybe they were aware of these kind of limitations that I'm going to talk about on this slide. Maybe not, but it seems like a typology of quantum gravity theories along the lines of the Butterfield-Eischen one. Yeah, it does have a lot of limitations. So one thing is that the types aren't really mutually exclusive, like a lot of modern quantum gravity programs seem to me to kind of combine features of various of those categories. So maybe loop quantum gravity could fit in multiple of these categories, group field theory. Yeah, one thing is also the typology is flat, so it is sort of intended, I think, to be mutually exclusive, even though it's not. But I would think that a multidimensional typology would be better, because this flat typology seems to overemphasize certain concepts. Like I said, quantization and the classical limit play a big role in the typology that they give there, and it's probably too general relativity centric. I mean, they're thinking of things, I think, more from a general relativistic point of view. So either general relativity is a starting point or it's not. That's the kind of basis of the typology. And one thing that is also suggested by the typology is that recovering general relativity in a low energy limit is like the important success criteria of a quantum theory of gravity. But you might suggest that there's really quite a wide range of success criteria involved in developing a quantum theory of gravity, whether these could be unification or accounting for semi-classical effects, accounting for black hole thermodynamics, the laws thereof, singularity resolution is already mentioned, and so on. Yeah, and so one question for you quantum gravity people is there any use for an improved typology? This is the only one I know about personally. Yeah, and if so, then yeah, I guess it's an interesting idea what a typology like this could do for aiding research in the field. Okay, so this was just the first thing that I kind of thought of when I was trying to think about quantum cosmology based on a quantum theory of gravity, is just to get some sense of the playing field, which is quite complicated in quantum gravity.
Do you want to discuss it, or?
Well, yeah, I mostly presented this as a point for discussion. We could do that now or later.
As you prefer.
Yeah, why don't we do that? I mean,
Can you just show the typology?
sorry?
Can you go one slide back so we can do the...
Yeah. Yeah.
So to answer your question, this is not the only typology. There are others. I think Stephen Carlip has one. I think Roger Penrose had at some point tried to give categories. I think I have.
Oh yeah.
In my PhD. Not that I would have put myself at the same level as these people, but they tend to be similar. They're not exactly the same, and
But do you find it kind
many of them probably are similar in character, that they would be similarly vulnerable to your points of criticism on the next slide, that they're somewhat geocentric, that the recovery of GR as a low energy limit or a sort of classical limit is taken for granted, which I think is, by the way, an absolutely well-motivated criteria of success. So even though there's some variation there, maybe it's not as much as you'd like.
Yeah. Well, I mean, I don't have a horse in the race, I guess, but I mean, one thing that I find curious about it, though, is that the typology is based on ways of getting a theory, which seems like an unusual way to categorize theories. It would seem like some theoretical characteristics would be the natural way to characterize theories, but I guess it's because we don't really have one. That we want to think about how to get them.
Yes, exactly. So there is really no completely formulated full theory of gravity there that really deserves that name. I mean, if you ask defenders of any one approach, they will disagree with that and think that theirs is the one exception to that rule, but I don't think that there is really an exception to the rule. So the debate is very much centered on how should we get there, get such a theory, what's the best methodology, what should be the guiding principles that we use, which kind of general approach do we take to get there. That's very much discussed, or at least was very much discussed, not so much maybe recently, but until like 10 or 20 years ago, that was the big discussion. And this is why people started to try and come up with these typologies and sort of try to sort of broadly cluster approaches that are at least similar to their general approach under these more general families of approaches, because there are so many.
Yeah.
And that seemed to be like a reasonable way to classify the approaches a bit.
Yeah, that's good, because that does play into what I want to say later about principles as a basis for theory development and so on, and the contrast that I want to make in the third lecture about the meta-empirical assessment point of view, which I think would look at this a little bit differently.
I think sometimes in the philosophical literature there's a bit of a distinction also either these principles versus fundamental versus non-fundamental. Let's say quantize GR, what does it really mean? Right? Does it mean to quantize non-perturbatively, which is somehow more ambitious than quantizing perturbatively? So I'm not sure this is reflected by this, but maybe one could just distinguish this one. But I think in the philosophical literature this is often distinguished also kind of ambition, especially with respect to fundamentalities. Unification is also.
Right. Yeah.
So sometimes people bring in these principles to sort this a bit more, right? But otherwise I agree. It's very much better. And sorry, just a quick comment because it comes to mind. You say it's kind of funny that it's kind of constructive, right? Rather than you are defining the things in themselves. You're defining how you get at them. With emerging gravities, like this is a specific approaches even like this. It's very hard to define what you mean by emerging gravity. You just define it as something where you don't quantize. Well, positively you say it's some kind of a mean field approach maybe, but even that doesn't seem to be absolutely correct. Maybe it has something to do with thermodynamics or so, or hydrodynamics. And so often it's more like you define negatively and constructively. Say something you don't get at by constructive through quantization. Sorry, this is small for you.
No, that's great, yeah. Okay, so maybe I'll go on a bit then, unless there's more to discuss on it.
Maybe about success criteria.
Yeah.
On the next slide, there is a bit of a literature about that as well. I mean, at each of these ones. So unification is not so much a topic anymore, but back when, James Mattingly and Nick Cockett and Craig Callender and Jeremy Butterfield and all these people thought about whether it's necessary to quantize gravity. That was often discussed in the sense of unification, because if there is unification, if unification is a basic principle, then it seems like you have to quantize it. So, this is why people...
what I find odd about that though is that, like most quantum theories we don't get by quantumization. Maybe in some sense that's true,
right.
But when we think about successful theories that are part of, say, the standard model, that's not how we got those theories.
Okay, but all of these are quantum theories.
Right.
Whatever it is, quantization or something else, you get them. But surely, if a unified theory was going to treat all forces in the same way, it would be difficult to imagine that it doesn't. Anyway, so back then that was discussed a lot, and most philosophers agreed that unification per se is not a very convincing theoretical success criterion, because the universe might not be unified that way. And black hole thermodynamics more recently has, there's some philosophical literature about to what degree that really, should be, what the status of black hole.
Then we're in a difficult situation, because every time we put a principle up, philosophers are going to come and say, well, it doesn't seem like that's really all that necessary. And so then we don't really have any principles to go on.
That is a bit, yes. It's not completely wrong, actually. Yes, this is a bit what happens. And singularity resolution, of course, is a big thing as well. And some philosophers even have contested that, even though I think many accept it. That this is if you have a theory with singularities, or at least with singular models, then you have a problem.
I think much of the literature is also kind of gadfly literature, people who just want to be annoying. I mean, they know they can have a logical point, but I think more interesting is kind of, you were kind of suggesting to look also the history, like which principles turned out to be useful, which were actually used back then. And then, I don't know, but logically you can always attack any, And the same with vector dynamics, right? There's also a lot of points which got made by people recently that kind of, without also just zooming in. In Fenner, I can do this with zooming in and then just pretending one doesn't know anything else anymore about this, and then,
Exactly. This is how much philosophy of physics works. You're a gadfly into the physicist's ear, or where is my gadfly, or whatever. In the
Side.
on their side.
On their rump.
Okay, yes. Anyway, so many of us think of us as our role, and then David Wallace is the higher order gadfly. He thinks of himself as the gadfly in the rump of the gadflies, I guess. Yes, that's what he once told me.
Yeah, well, I mean, as far as principles go, okay, I have a little table here again, but before I get that, I did want to point out, when we move from quantum gravity to quantum cosmology, so far I've been talking about the move, just like how general relativity moves to relativistic cosmology. We think of once we have a theory of quantum gravity, even if it's not fully developed, we can maybe apply some of those insights in a quantum model of the universe. But I was reading through a fairly recent book on quantum cosmology by Kiefer, and he sort of suggests some motivations that come from standard cosmology towards a quantum cosmology. So, for example, the first one, the lack of experimental feedback makes it difficult to discriminate among different models of quantum gravity. Everyone knows that, and to characterize them as falsifiable. But it is natural to turn to cosmology in an attempt to bridge this gap and advance our knowledge. So by looking at cosmology, we might have some ideas for how to develop quantum theory of gravity. It's a suggestion. But however, on the other hand, when we look at the concordance model, the lambda CDM model, it's a great model. It fits all the data without compelling need to invoke any more really exotic physics, supersymmetry, string theory, quantized gravity, and so on. It doesn't really seem to need a quantum gravity theory at large. However, certain ingredients create a sense of uneasiness in the research remaining for theoretical reasons, and by this he's referring to things especially like dark matter and dark energy. And so we get then a kind of thing like, now we have theoretical motivations coming from well, some of the ones we talked about, I didn't put that in this slide, I would have required another category. Something like, I guess from model to theory or so. But supposing we do have a quantum theory that's universally applicable to gravity as well, then that would naturally lead us to a theory of quantum gravity. But the Kalkani quotes are suggesting also that there's certain model assumptions or model characteristics that exist in standard cosmology that might feed back into quantum gravity. I'm not sure how serious these things are in a way. I'm sure people are working on these, but in some ways it sort of sounds like, well, we don't know what this is and we don't know what this is. It's probably related to quantum gravity. Or like how people do with consciousness. We don't know quantum mechanics, understand quantum mechanics, we don't understand consciousness, they must be related. So anyway, there's a kind of empty sector down here, of course, which is one of the main problems with quantum theory of gravity. And so that naturally leads people to look for theoretical motivations on how to develop the theory. The theoretical motivations, although, as we've been talking about, generally get represented as certain principles, as sort of guiding threads to quantum gravity. And what I'm hoping to do in the third lecture is suggest a maybe alternative way of thinking about the development of theories in a more, in a sense, empirical or meta-empirical point of view. So that might circumvent some of the problems of thinking of things in a principle-based way. The principle-based way seems to me largely motivated by thinking of things in a logical way, in a deductive logical way, where we think about principles and deducing things from them. And I think the meta-empirical analysis takes a different kind of point of view, a more kind of inductivist point of view how to make progress in science. Anyway, so just to talk about a couple of the principles that, by way of having examples, one is singularity resolution. Just a little bit of history here. So in the early history of general relativity, probably as many of you know, there was confusion over these apparent singularities in the cosmological models, and that did hamper development of cosmology at the time. And it turned out that many of these were just coordinate singularities. They appeared because of an inappropriate choice of coordinates. So I know this story best from Ehrman's book, Bangs, Crunches, Whimpers, Shrieks. In the next chapter, he discusses the singularity theorems, which were a big event in the late 1960s. So Penrose, Hawking, Alice, DeRoche proved various theorems that demonstrated the irremovable presence of singular behavior in certain cosmological models, in particular, Schwarzschild, FRW. And this suggested from a physical and mathematical point of view that singular behavior is an endemic feature of the theory of general relativity. And it does feature in the standard model of cosmology, their singular spacetimes. Even if you remove some of the symmetry assumptions, like FRW models are highly symmetric, uniform spatially and so on. But even if you look at perturbed versions of that, the singularities still exist because you do have the focusing of geodesics. Okay, so then, as I mentioned earlier, and as you also well know, many programs in quantum gravity and cosmology too take singularity avoidance to be a key desideratum to any successive theory of general relativity and the concordance model. Okay, yeah, and so, part of then making this a desideratum is saying what a singularity is so that we know how to avoid it. And it's still something that's debated a little bit what the best way to describe singularity is. So, making use of a paper by Bojowald from 2023, who takes up this question: what are the success conditions for singularity avoidance? He takes up a certain point of view, but says that this is a set of conditions that we can reasonably expect need to be satisfied in order to say that we've avoided singularities in our quantum theory of gravity. So geodesic completeness, classical limit, unitary dynamical evolution, finite expectation values for physical quantities, no pathological space-time solutions. These all sort of approach what a singularity is from a somewhat different point of view. But a theory that did all of these things, at least in argues, would be a kind of theory that we could say is a theory that avoids singularities. Here's his paper here. And I put up this introduction because it seems like he takes as given that singularities are a problem in theory, in general relativity. Right? Observable quantities stop behaving in a physically reasonable way. Singularities are physically unreasonable then. He talks about the singularity as a local curvature pathology. Pathology, that's a problem, right? It's something that's wrong with the theory. And I don't know, maybe I'm out of date, but I always thought that singularities weren't such a bad feature. I was convinced by reading Ehrman's book and so on that, you could take different attitudes on it, but the theory, just because it has singularities in it, doesn't mean there's anything necessarily wrong. Like our model is perfectly good for cosmology, for all the possible applications we would want for it. Yeah, there's no point where anything breaks down or goes wrong in general relativity in the FRW model, for example. Yeah, so anyway, though, if we take singularity avoidance as a basic principle, as Crowder, especially his written papers talking about singularity avoidance, especially the one with the Haro, the singularity avoidance as a principle can play different roles in developing a quantum theory of gravity. So earlier we were talking about quantization as a basis of a typology for quantum theories of gravity. In a similar way that you think about what role quantization plays in the theory, you can think about the different roles that singularity avoidance might play in the genesis of the quantum theory of gravity. So they suggest a few different options, maybe even a fourth one, but maybe you know better, but maybe it's just these three. So you could just implement it from the beginning as a sort of structural feature of the theory. You could regard it as something as a check at the end, like you develop your theory, see if it avoids singularities, and if so, then you can say, oh good, I've made some progress here. Or you could say, well, it's desirable, we might like a theory better that doesn't have singularities in it, but we don't understand it as a theoretical constraint. And you can maybe fit different programs in quantum gravity into these categories, depending depending on how most people or certain key people think about singularity resolution and its contribution to the theory. But I'm still left with this kind of logical question we were talking about earlier, like why is it playing a role in quantum gravity at all? And in particular, like what evidence do we have that makes it likely that singularities are going to be avoided in a successor theory to general relativity for gravity?
I think there may be a stronger motivation for that coming from black hole physics rather than cosmology, because in cosmology you could say like, yes, it's not, the model is not really singular in the sense that there's no location in space-time at which the pathology sort of is located or something like that. It's sort of a limit, right? You cannot go beyond that. But in black hole physics, if you look at co-Newman spacetimes, for instance, it's not so obvious you can do that because there are pretty straightforward ways in which you can extend these models into perfectly analytic continuation of the spacetimes, but then it becomes odd to have like a ring-shaped singularity somehow in the middle of it, which is not like a limit in a sense, but really there is a singular ring which is in some sense localizable. And that seems a little bit weird. Even though, strictly speaking, there, of course, we don't have, the manifold doesn't contain the singular ring. You could still put yourself in the point of view that this is, there's nowhere where physics is singular, but it becomes somewhat more difficult to from a physicist's point of view, not from a mathematician's point of view, to defend. And this is why I think physicists feel that this is not the correct representation of the physics of a black hole. So what this language really means is we need to get the correct physics of a black hole. And there shouldn't be oddities like that.
No. Yeah, it's clear methodological, philosophical assumptions, and I think going into that way of thinking.
Absolutely, but I think they're widely shared by
Yeah,
physicists.
No doubt.
Yeah.
Okay, and then the second example. Oh, yes. Oh, sorry.
Yeah, I think there's sometimes like what kind of singularities we're talking about. I guess like the expectation of like quantum gravity is something for singularities is specifically in the case of like strong complementary singularity usually. So like black holes, like Big Bang, and I guess like one of the motivations is, oh, these are the domains. Like we have like good reason because like even like just looking at mathematical theory, we have good reason that these are the domains in which we have both gravitational and quantum effects. So in this sense, like quantum effects are not cannot be neglected anymore. So we need theory that also takes into account quantum effects. So in this sense, I think like it's not like maybe any singularity that we have good expectations because of quantum gravity, but there are like some specific examples of like black holes, the Big Bang, in which we have good reason to think that like something is going on, like in the field, like there is some physical phenomenon, let's say, is going on, in which we need to take into account what relativistic and quantum effects. So in this sense, natural candidate is quantum gravity, like a theory of quantum gravity, which is supposed to do both.
Yeah. This just sounds very heuristic to me, I guess. I mean,
I think it is.
Yeah.
I think it is. Yeah.
Maybe it's somehow related. If I answer correctly, so there's certainly regimes where you wouldn't expect GR to hold anymore, right?
Yeah.
And you could say, typically, if you have singularity somehow local, and you can really look at it, but you can say it's not here, it's not here. Somehow you can attach it to some region, maybe there's this disagreement but then you could say that it is a reason that the theory doesn't take anything, so maybe we don't want to avoid singularities, but we just want to keep there's certain regimes of the theory where we know that the theory breaks down. There's certain part of the model where we know this doesn't hold anymore, and then the singularity is just, so to speak, the proxy for this statement somehow. Is this what you were saying?
Is that what you're saying? That it's just a proxy for a statement that...
Anyway, I would like to ask...
But then if you insist on something like singularity avoidance, that seems like that's not just...
Right.
Yeah, I don't know.
Maybe this is a good reason to say, we shouldn't take these people literally that they really want to remove singularities.
Well, I mean...
No. Then yes, a lot of us yes, but physicists, for example.
Maybe in other cases.
Maybe what's really, but one should just distinguish is between, in what context these singularities occur. They usually occur in the context where we know we cannot trust the theory there anymore, and so it's kind of we become sloppy and just creating model that doesn't really apply anymore, or we have to, and singularities, and then some philosophers of course pick it up and cements this.
Well, the idea of trusting the theory plays right into the meta-empirical assessment story.
Yeah.
But then you shift, then the problem is the shift to the principle-based thinking. As I'll try to argue. You sense the problem, but then you think, how I solve the problem is taking a very strong assumption, which I don't have very good reason to think is correct in any future successor kind of theory.
I think the test would be if we had a successful, empirically confirmed quantum theory of gravity, which would give us a completely physically acceptable theory of the very early universe and of black holes, and yet it turned out that it contained singularities, in some sense singular. Would the physicists be fine with that, or would they still want to?
I think most would, some wouldn't, and then they keep on trying to make these...
I don't know what they actually would. But that scenario, when I was to pick these two possibilities apart.
So just to clarify, are you agreeing that the criteria for what's physically acceptable is what would be accepted by the majority of physicists? Seems reasonable, but I just want to check.
If something is accepted by a vast majority of physicists, I think that that's relevant evidence for sure, that something is physically reasonable. But I wouldn't accept it as conclusive proof, because I do want to accept the possibility that they're all wrong, even though they agree on something.
Okay, and I mean, sorry, this is probably something you can't explain in one line, but in the black hole case, part of the reason that you think it's more striking, now apart from what physicists, that you think it's more striking, is the ring part, that it's somehow, that it's not even point-like. Did I understand that correctly? Or no, it's something much more complex about how it comes about and the dynamics of the entities would be, right?
So in some sense, mathematically it's ring-shaped, and you can think of the entire world as being up here. Then you come to this ring-shaped singularity, and you can actually go through mathematically. So this is mathematically this level here. This surface is the surface of zero distance, but you could go to negative distances. Mathematically speaking, you can extend to minus r, and you see that there's like a mirror in, not quite a mirror, but you could continue anyway, the space-time over here. And you could sort of, in principle, you could go through. It seems like there's no physical, nothing to stop you from going through into this other world. And there's a domain in which you can time travel, which is around that ring singularity. It's like a ring-shaped region where you can go in and you can time travel, and weird stuff happens. And the the reaction to this kind of mathematics for most physicists is like, okay, that's really cool. Mathematics and philosophers get all excited about the possibility of time travel and so on and so forth. But we as physicists think something's going wrong here completely.
Right.
This is not
Okay.
giving us a physically correct model of the physics of the black hole.
And insofar as you were commenting on that, sorry.
Maybe in the cosmology case, that case is not as strong.
Yeah.
I mean, you know that you go back, you know, the curvature gets arbitrarily high, the density of the energy or the matter gets arbitrarily high. That seems a bit unphysical, but maybe it's not quite as strong.
That's somehow to do with infinities, merely.
Well, but at no point you get to actual infinity.
Right. And so insofar as you were commenting on or reacting to that whole thing so far, you were saying, like, did I understand correctly, you were separating the sense that there's something wrong, that we don't have the means yet to model this accurately, from the further step that the reason we can't is because there's a singularity. Yeah?
I think so, yeah. Okay, so there's just, like, I wanted to have a second principle to talk about. There's many more that one could, but I don't want to go too far. This is one Niels has worked on about UV completion. Yeah, I think maybe in the interest of time, I'll go through kind of quickly. So, well, yeah, what to say? Okay, yeah, I mean, just to say the things on the first bullet, at least, quantum field theory is UV complete if it's well defined at arbitrarily high energies. A theory that's regarded as an effective theory is one that's only valid up to some energy scales. Here's some examples to differentiate them: QED, QCD, gravity. It gets more complicated because we can think about things perturbatively, non-perturbatively, and so on. And yeah, but yeah, given the examples already here, we see that UV completeness is not a requirement for a successful QFT, successful in the sense of acceptable by the majority of physicists anyway. But clearly it is a significant property of the theory to possess. Like if we find a UV complete theory that's empirically applicable, we think that's quite nice. Just like if we, I think, found a theory that was free of singularities like the ones in general relativity, that's quite a nice property to have because of the various advantages that they give us. Okay, so again, just like with singularity completeness, UV completion is taken to be a key desideratum in certain theories of quantum gravity, with quantum gravity. As an example. So again, just as with the other, singularity avoidance, UV completion can be seen to play different roles in the various approaches to quantum theory of gravity. I think you took this from Crowther's earlier paper too, like these 3 different ways, right? Yeah, so you know, it could be implemented from the beginning, could be regarded as an important check, could be desirable, understood as a theoretical constraint. And you know, actually I didn't compare the previous one to this one, but they're not in the same category, so I think it's different programs assume different constraints, as it were. Yeah?
I would argue the other paper has taken this from this paper.
Oh, really? Okay.
No,
Sorry.
because isn't it the time?
I thought that was the earlier one. This is the earlier one.
This is the earlier one, yeah.
Yeah,
I'm just saying.
Okay, you took it from this one. Okay, good. Yeah. Okay. And so yeah, the big point of Crowther and Linneman is that UV completeness is unnecessary and artificial as a guiding principle in modern physics. The logical point that is surely correct, right?
This is from 2019. I have to say these
Oh, you changed your mind.
I did not change your mind, but it's kind of really part of this logical discussions, right? I mean, I just said I can talk about it more, but I just speak first.
Yeah, let me just finish up that. Okay, so yeah, well, to add on to what I just read on the previous slide, so they argue that UV completion is poorly motivated as a guiding principle in theory construction, cannot be used as a criterion of theory justification in the search for quantum gravity. There's no requirement for quantum gravity be valid at arbitrarily high energy scales. So again, like we see as a principle, UV completion is not a necessary condition. Which is not surprising because like where are there necessary conditions in theory construction? Okay, so maybe by necessary you meant like strongly motivated or something. But anyway, a lot of the principle-based thinking I think falls into this kind of basically logical kind of thinking, looking for necessary and sufficient conditions. And of course, for anything in physics, we're not going to find those kind of things. So again, I think, well, what kind of evidence do we have, or can we obtain that would make it likely that quantum gravity is UV complete? That's the kind of, a different kind of perspective that I think is the perspective I'm going to again say, I think in the last lecture about meta-empirical assessment is trying to think about how we can gain evidence about what the shape of various theories is or could be. And maybe that sounds crazy right now, but I hope to make that plausible. Okay, so yeah, again, like leaning on some of the stuff that Crowther's written. So she starts off this 2021 paper by saying, in times of crisis, when current theories are revealed as inadequate to task and new physics is thought to be required, physics turns to reevaluate its principles and to seek new ones. I don't know if that's empirically true, if we go out and see, do physicists actually do this, but yeah, it's plausible, I guess, that physicists may think of things in a principle-based way. There's plenty of evidence because physicists do invent principles and so on. But you know, what physicists write and what they say may not be exactly what they do also. And so, well, I'll get into that when we talk about meta-empirical assessment again. But again, like, you know, principles can be divided in these ways, guiding principles. But why take any principle as a guiding principle? You know, why trust a principle as a mere heuristic guide? Okay, maybe it solves a certain problem for you, but is it a guide to an actually empirically viable theory or not? That's the question we want to ask. And heuristic principles usually don't have that character of being, you know, we don't have good reason to expect a heuristic principle to be successful. It's often just a convenient one. Why we can make postulates, but why postulate something that we don't know is viable or that we don't have evidence to expect to be viable? Well, it might be because we don't know and we're just giving things a try. But then that's a certain kind of epistemic condition that we're in, a condition of theoretical uncertainty. And how we develop theories depends on what kind of epistemic condition we're in, I think. If it's a complete uncertainty, then maybe we want to just try heuristic principles, try postulates, but we don't have much reason to expect those to work. And so those postulates or guiding principles aren't really based on evidence. Yeah. Anyway, so what I'll try to argue in the third lecture is the best reason to trust a principle, at least in certain empirical contexts, is that it's probably correct. And the only way to assess that is on the basis of compelling evidence. What kind of evidence is different than the normal kind of evidence we look for in physics when we talk about confirming predictions and so on. But I think we have to accept that there is a basis of compelling evidence for even these theoretical principles if we want to suppose that science is not just a mere guessing game, and that it's not just constituted by some sort of logical system with necessary principles. We have to think of things in a more inductivist way. Yeah. Okay, so that's what I'll end the lecture today, as a prelude to what I'll say later. Okay, what's the plan now?
We are very flexible as far as the scheduling is concerned, so we can either continue the discussion over it here, or directly go for coffee.
I need a drink. We're talking so much, so yeah, I think we go somewhere. I think that would be somewhere I could have something to drink.
Okay.
And can we just continue for like 15 minutes?
Yeah. Well, if someone wants to load me some more, you have something? I think we can continue.
Yeah, and somehow it's easier to discuss here rather than if we are sitting on the table and
Yeah, so we can continue for a little bit.
Well, it's an open discussion, I think.
Yeah. We don't have a chair, so people, that doesn't make much sense. People hold up the hand and wait for the chair.
We all have chairs.
That's
Too
true.
many chairs, it's the same as in no chair at all.
About the recognition. I still think it's fair to criticize what people are just implicitly assuming a principle like this, right? Why do they need to construct such a theory, which is UV complete, after all, a truly formal property, right? And often it seems because they're very ambitious, they want to have something rather fundamental, UV completeness of a couple to that, right? So that's it, I agree with our paper from 2009. But I think what's interesting, if you really look at QFT specifically, you see UV completion, the failure of UV completion doesn't only entail that the theory stops to be predictive, but also you will get at some point breakage of unitarity. So the problem that GR is non-renormalizable, this I only learned from Wallace at some point, is not just that it's not predictive, but also that eventually unitarity breaks down. And so it would be one thing to say you lose, okay, the world might be like this, that you lose predictivity, but this might be a fundamental theory of the world, that you have this EFT, for instance, right? But if then also unitarity gets broken, then a lot of our understanding and interpretation of the theory also gets lost. Okay, you could say again, why do we need to have unitarity, right? But especially in the context of GR as an effective field theory, I do find it by now very unattractive that this is not really complete. So this is a more correct one. This is more like a technical point about one specific theory which is not really complete than about the necessity to have unique completeness in general. Sorry, maybe this will not be it's just, yeah. I don't know if you remember in this paper we have this kind of option where we say, oh, it could be EFT all the way down.
Yeah.
And I think this suffers a bit from this objection you could make about, but especially can we be GR as if you EFT all the way down. This can already be given the unitarity breakage and thing it seems, but yeah, anyway.
So I have a general remark about this sort of a dialectical situation in these kind of discussions. I completely agree with you that of course it's silly to think that any of this is a necessary conditions, strictly necessary conditions. Nobody is under the false problematic illusion that somehow this has the same rules as logic or mathematics or something like that. Of course, these are not principles of any necessity comparable to those of these formal languages.
Of course, you make some pretty strong statements.
But I think historically, at least, it was still important also from the philosophers to point these sort of things out, because sometimes, at least in the rhetoric of physicists, these principles have been presented pretty much as if they were necessary principles, and as if there's really no alternative. Of course, much of this is rhetoric in the service of promoting their particular approach at the end of the day. And I think that the useful role of philosophers who are not tied or paid by any of these research programs was then to say, like, hang on a minute, there's really nothing necessary about the criteria you're using. There could be completely different ways of doing physics. Let's not forget about that. So let's, in a way, maybe the much more reasonable and measured, but important point is that a negotiation of these principles is important, but an important part of that negotiation is a consideration of the status, so the epistemic status and force of any of these conditions, of which, unfortunately, there's not often, or not all that much in the literature by the physicists themselves.
And I think there's also probably a difference between saying, oh, this is not logically necessary, and so you should just in general think about doing it differently, or this is not necessary, and also there are other candidates which could do what you want to do without that, right? I mean, and that's for instance the case with UV completeness example. I mean, it's not just one just point out, oh, logically you could also do without UV completeness. Sorry, I don't mean it as a counter to anything, just a statement. But no, we really did. There seem to be live options, and similar, I think, as the kid was doing about gravity and quantizing, right? It's not just saying, oh, it could be logical possibility not to quantize, but I think there's also this live option of simultaneous gravity at the same time around, which some people do say it could work. Although, I mean, you've learned at some point from Rainer Fäch, the hard way, this is more than a live option, right? But anyway,
Yes, and I think that's important to keep these points in mind.
I want to add, well, to clarify my point on symmetric solution, in the sense that I agree it's not, I don't think it's But what I mean is that in some cases, in some like example of, especially like the early universe, we already know that there are like important quantum effects from, let's say, other like outside reality, like from Big Bang nucleosities, from particle physics. We know that like this is a regime in which quantum theory is important. Or like it's, I mean, we should take into account quantum theory. And in this sense, the idea is that when we approach the singularity, the more we approach the singularity, the more the energy is high, the density is high, and so on and so forth. So probably like GR being a classical theory is not enough to provide a reliable model of the physics, for example. So in this sense, what I wanted to say is like we have reason to think that GR is strong, and we have reason to think that probably we need a quantum theory of gravity because we already know that in this domain we have quantum effects and relativistic effects. So we have like kind of independent reason outside of, let's say, not coming directly from quantum gravity, but like coming from like all the other physical theories that we have and that we are applying in that domain. So in this sense, I mean, I don't know if it's like stronger than just saying, oh.
Well, I feel like I agree with everything you said. I mean, a way of saying is, near a singularity, we expect quantum effects because of what we know about quantum theory. Those aren't predicted in the theories we have now, so we should try to find theories that might tell us what's happening in this area. But yeah, it does seem like one extra step then to say it's because of the singularity that we are not able to model these effects, and if we remove that, then we'll have them or something. That's just a guess, it seems like to me.
Yeah, I mean, yeah, so it depends what you mean with singularity resolution, I guess, because in a sense, like I mean, like probably like all the people working there mean just avoiding the singularity, something like this, but a resolution could be something like replacing this singularity with another description which approximately, you again have singularity in lower energy regime, something like this. Which is, I mean, might be like, I don't know, slightly different.
Well, I mean, there's one kind of intuition behind that, like, the problem is that there's, like, something like missing points, so our theory is incomplete, and the singularity just represents that we haven't a complete theory yet. And so, by removing the singularity, we'll have a complete model of the world. That's one idea that people might have. And then by removing the singularity, now we have a model that covers all points. But I mean, that's not accurate, like mathematically accurate anyway, if we're talking about singularities, because in a sense all the points are there. There's no missing points.
Yeah, but like so for example, like the criteria that both in the paper, like geodesic completeness on low energy or unitary evolution and so on. These are like some indication that.
But that has to do with our expectations for what a theory should look like, then, I guess. But GR, in a way, has taught us that theories can look very different and be very empirically successful. So why should we just go in with assumptions about what a good theory should look like? We have to learn over time through science what a good theory looks like. And sometimes theories disappoint our expectations about what a good theory should look like. Right?
I mean, yeah, I mean, I don't know, I guess like, so one point would be like what Chris was saying, okay, so we have a theory of quantum gravity, and we have singularity also in theory of quantum gravity, then our expectation fails.
Mm-hmm.
But I feel like, I mean, this is an option, but like otherwise, the idea is that in any case, the description of the singularity is going to be replaced by something else in the theory of quantum gravity. As, I don't know, as we will probably not have the concept of geodesic in the theory of quantum gravity, so we will have something else. So we will not even talk about geodesic completeness or incompleteness. So in this sense, I think like the singularity, well, will be solved or resolved or it will vanish somehow in the sense that like the physics itself is not different. So we will not have like exactly the same thing, we will not have physical completeness, probably we have the theory of quantum gravity. So in this sense we will solve the singularity. But maybe we will have like other types of singularity in the theory.
Mm-hmm.
You know? Like these acceptable. But like my point would be probably we will not have like a Big Bang singularity in the sense that we have the GR. Exactly because GR will not be applicable to that.
But where do those expectations come from? Your expectations personally?
Well, to the fact that we have quantum effects. Maybe I'm not. I can try to explain myself. But,
Yeah, I mean, I guess one issue is, in general, it's just that general relativity is kind of a weird theory with respect to classical theories, because in the past, singularities were places where things went to infinity, and those were bad for physical reasons, but the singularities in general relativity aren't like that, because it's the space-time itself that's singular. And so I just feel like we don't have a very strong intuitions for what successor theory would look like with respect to that. Like, should we be able to recover that? Maybe.
Quite the opposite. I think actually GR in a way gives us evidence to think that maybe singularities are physically relevant. I mean, in a twisted kind of way. Initially, physicists did think singularities are problematic and need to be excluded. So if there's any model in GR that was singular, that was automatically considered unphysical. Like Einstein, 1917, 18, while all these people back then discussed these things. This was automatic. They just knew singularities are bad. Our theory has gone wrong. This is cannot be good physics. But then it turned out first that some of these singularities vanished because they were just apparently due to a bad choice of coordinates. So that has nothing to do with the physics. So let's look at the geometry, E, but that's still a problem because some of these are not coordinate artifacts. And in fact, then it turned out in the 1960s that many of the physically most relevant models of GR are singular. And by that moment, it's like, gee, yeah, that's evidence that maybe we should in fact look for theories with singularities in some kind of that. I mean, nobody would go as far as that, but that really complicated how physicists had to think about singularities. So, what do we do with that? And for many physicists, the fallback position was then what Berkman would say, if there are singularities, that's the seed of its own destruction. I mean, that cannot be a fundamental theory, really. That's just a good approximation, working well for some regimes, but breaking down somewhere. And the singularities are like a sign of that. So that means we need to go to a more fundamental theory. And I think many physicists have taken over one version or other of that kind of thought and accepted that singularity resolution, our fundamental theory is going to be free of singularities. But I don't know. Maybe not. Should we take a break?